There's another talk I used to give that David doesn't know about. It was called Dating a Young Star. And when I gave that talk, this was the first image I would show. This is the Pleiades cluster, an open cluster in our galaxy that's about 150 million years old, something that I actually worked on finding the age of. I'll talk about some of this, and this will be a recurrent image in my talk today as I go through how stars actually die. And so what I want to do for you this evening is talk about exploding stars, and the first thing I want to do is teach you all how to count. So in school, you were probably taught 1 Mississippi. Who was taught that? I was taught that. 2 Mississippi, 3 Mississippi. So now you're going to learn the new way, which is that in our universe, it's 1 supernovae per second. So you want to now count, everybody ready? 1 supernova, 2 supernova. Okay, that's the way it works in our galaxy, in our universe. And because of, and I'm going to talk about today, the reason this is an exciting field is that we're now finding about 10 of those per day. So there's still many more to discover. We're now getting up to around 10 per day. And just that alone, of finding 10 per day, or a few thousand per year, has really led to a tremendous amount of diversity in what we see. And that's what I want to talk about this evening, is the many ways in which stars, as they die, reveal themselves to us, and how that is starting to teach us many things that are quite surprising. So I'm going to really emphasize that this evening. As usual in science, the work is not done in an isolated manner, and so I've listed here the collaborators that I've been working with who are either graduate students, postdocs, who have worked with me in the last 2 or 3 years on many of these problems, just to remind everybody that it's not just myself. It's actually a very large effort of many people all working together to make progress, mostly theoretical, is what I'm going to talk about tonight. Well, so this is the headline. I don't need to tell you this. Everybody knows it's all about energy. We've known that in stars for a long time. And what I need to make clear is that there are really 2 types of energy we're going to typically talk about using in stars. And we use them both in stars like the sun, but we're also going to use those energy sources as well when stars explode. And so the first energy I need to remind you of is gravity. It's an energy source to us, because if a star contracts upon itself, shall we say, slowly falls into itself, that's releasing gravitational energy, just as if I dropped this and it hit the floor and the kinetic energy of that collision radiated. That would be a release of energy. And so gravity is one way in which stars radiate. One source of energy is going from a large radius to a small radius. And this energy source can get quite large, as I'll talk about, in very late stages of stellar evolution. The other energy source is the one you're probably more familiar with when you think of stars, which is the release of energy from the fact that in the Big Bang, all that's made, as they say, all that's made, is hydrogen and helium, a little bit of lithium, a little bit of beryllium, mostly hydrogen and helium. And as that material coalesces, forms stars, it starts to undergo fusion, in particular in the sun. What's happening at the center of the sun is the hydrogen is fusing to helium, and that is an energy source that allows the sun to live for as long as it will, another, say, 5 billion years, much longer than this talk. And of course, as I'll remind you today, that's how heavy elements are made. Carbon, oxygen, everything basically above helium is made from fusion in stars. So the first difference I want to make clear is how stars really do behave differently as opposed to when they explode. So something like the sun is hot at the center, it's cold at the surface. It's not that cold, but it's cold relative to the center. The center, it's 10 million Kelvin. It doesn't matter what the units are, it's a big number, okay? 10 million Kelvin. Yeah, you can ask me Fahrenheit, it doesn't matter. Okay, this room is 300 Kelvin. The center of the sun is 10 million Kelvin. The surface is at 6,000 Kelvin, but it's much colder at the surface than at the center. And because of that, heat leaves. Just like when you turn your heat on in your house, trying to warm your house up, of course what you're really doing, you all know this, is you're warming up the outside. That's what you're actually doing. And you pay a high cost, and if you insulate, you don't have to have quite as big of a gradient. And that's all a star is. It's very hot at the center and cold at the surface. Derek?
So I'm partly asking this question to remind people that this is not a public lecture, but a chalk talk, and it's legal to interrupt and ask questions. But my actual question is something I've never thought about. That as a star collapses, you say it releases energy. Is that one of the sources of gravitational waves? Is the energy, the gravitational collapse leads to the expression of gravitational energy?
Not gravitational waves, no. This is the fact that as the material gravitation, we call it contraction, very slow. Let me just say how it works in a star. When stars are born, and in this, I'm not going to be able to identify one in particular in the previous image. When stars are born, they live for a very long time just by slowly contracting. And the energy source is just the fact that it's more tightly bound when it's smaller than when it's large. And that's the source of energy. And a star does that until it gets hot enough at the center that it actually says, you know what, I can stop contracting now because I'm so hot I can actually successfully fuse the hydrogen to helium. And so the way stars work is that they're hot in the center, they're cold at the surface, and therefore they radiate. They're losing energy. And if it's losing energy, it has to have a source to match it. And one source is that it slowly contracts. The other source is that eventually it gets hot enough to actually burn hydrogen to helium at exactly the rate needed to match what's coming out. And then it stays there and lives until it's out of fuel. And that's what we're going to mostly talk about, is how stars behave once they run out of fuel. So stars do this very gently. They live for billions of years. Supernovae, which I'll explain tonight, actually do the opposite. They release these energies, gravity or nuclear, so quickly that the object actually has no choice but basically to blow itself apart. And what I'm going to try to explain is why is it stars get themselves into this predicament. And they get themselves there because they must find an energy source. That's their job, because they're losing energy at the surface. They've got a problem. Okay.
Typical rates of contraction?
It totally depends on the mass of the star and where it is in its life. So something like the sun started with a contraction time of 1 million years, and it was decreasing its radius by a factor of 2 every million years. But it was very large at that time. And if you turned off the fuel source at the center of the sun, if you somehow could shut off fusion, it would start to contract on a time scale of about 10 million years. That's actually how we knew, once we had age dating of the Earth, and we knew that the Earth was not 10 million years old. That's what told us that we had a question as to how the sun was surviving. Because in the absence of knowledge of fusion, your expectation would be the sun should be contracting roughly in 10 million years. It should be decreasing its radius by a factor of 2. And it wasn't doing that. Or more importantly, we knew that that the age of the Earth was much longer, and so this energy source is much more efficient than gravity.
What's the heaviest element that it can be fused?
Iron. So let me do that. That's the next. This is perfect. Yeah. So perfect segue to the next slide. Okay. So you've all had your course in stellar structure now. Okay. So if you take a star that's maybe 10 times the mass of the sun, as it evolves, every time it uses a fuel up, hydrogen to helium, it's not hot enough to burn the helium. It's harder to burn the helium, so it says that's fine. All I have to do is contract a little bit more. I'll get hotter. Now I can burn helium to carbon, et cetera, until in the end you have this layer cake. This is a 15 solar mass star with mostly hydrogen and helium here. Here's helium, carbon, oxygen, silicon, and at the center, iron. Iron is the most stable isotope that you can reach via fusion. And so this ball of iron no longer has an energy source from fusion. And so that's a problem for the star, because at the center there is no longer an energy source. And this object, as it gets more and more massive, actually starts to collapse. And it collapses from a radius that's roughly the radius of the Earth to a radius of 10 kilometers. in about a second. Okay?
What is that number where it says 1.3 m?
This is a solar mass. This is M sun. So it's a ball of iron at the center, roughly the radius of the Earth. It's not on this plot, you can't tell. Radius of the Earth with roughly the mass of the sun, and it's extremely dense. It's at a density of about 1 billion times that of water. Okay? And it's at a temperature that's about 10 to the 9 Kelvin.
So, Lars,
Yeah.
I'm sorry to ask such a dumb question, but stars start out at this outer limit producing hydrogen and helium, and as they collapse and burn down, then they begin to produce carbon, and then in a later stage oxygen, so they're slowly collapsing? Is that what's happening?
Absolutely. So the center of this, when it was burning hydrogen, was only as roughly the density of water. And as it burns from hydrogen to helium, et cetera, it gets denser and denser during that whole time until it reaches this density, which is about 1 billion times that of water. Yep.
I'm reading this right, that from 15 solar masses down to 1, that's all energy?
I'm sorry?
It's all been converted into energy?
So from 15 to 4.2, this has been unburned, untouched material that's just sitting there providing pressure. This is an overlying layer. This is untouched.
It hasn't been burning.
It hasn't been burning. And then roughly at this place, inside of this is layers, all of this is burned to at least helium. Some of it's burned further, carbon, oxygen, silicon, iron. I feel like I didn't answer your question.
I thought that was mass.
It is mass. So inside of this is 4.2 solar masses.
Oh.
Inside of this is 15 solar masses. So there's 11 solar masses of stuff that's unburned. So it came on the star, and then it decided, well, you'll see in a minute, it's going to get shocked. It's going to have a shocking life. Yes?
What's that thing coming out of the star?
That's an artistic impression. So on the sun, and there's been great movies, some of you might have seen them from the Solar Dynamics Observatory. This is an artist's impression of what's called well, not a solar flare, but basically I forget what it's an arch or penumbra. I forget. Somebody remember? Huh?
Prominence?
Prominence, thank you.
Lars, this is what's confusing me and maybe others. Is this a time sequence?
No, this is a snapshot.
This is a snapshot right now as
Yep.
to what this particular
Yep.
body looks like.
That's right.
Okay.
Yep, thank you.
I see helium, carbon, oxygen, silicon, ... and some iron. Are there other elements between the silicon and the iron?
Yes. Yes.
They're
So
listed on the periodic table? Or
Yes.
how does that work?
yeah. So silicon weighs about half that of iron, so there's a lot of stuff between, and I didn't want to write them all down. So yes, and there are other elements in here, and the question, of course, is how does this material get out? I mean, this is really nice. It's sitting down here. It's carbon and oxygen sitting deep at the center. If we want to get this out, we've got to do something. Otherwise, we're not going to get this into our galaxy and into another star, or more importantly, onto an Earth or onto a planet and into your body.
Are you going to tell us where the heavier elements come from?
I'll tell you anything you want. Sure. Not right now.
Do they come from supernovae?
Yes, they do.
Okay, so that'll be coming.
Does radiation pressure contribute to some of that?
Absolutely. Yep. It's more or less.
In the final stages, sort of.
Yeah. Yeah. Okay. So the place of my story was that this ball of iron, radius of the Earth, mass of the sun, that's already pretty extreme, collapses down to 10 kilometers in a second. That creates a problem for the star. The problem for the star is that suddenly the bottom's fallen out. Right? And so all of this material tries to fall in. And the problem is that ball you've made at the center is so dense that the iron nuclei themselves are actually touching. And so you should think of this as a nearly incompressible ball. And as this material falls down on it, it hits it, bounces back, and leaves.
I see.
And so the source of energy is the gravitational infall and bounce and back that sends out what we call a shock wave all through this material. So if you're sitting at the surface of the star, you're having a nice day, then there's a sudden event which you don't know anything about, and then it takes about an hour for the shock wave to get to you. And when the shock wave hits you, you're suddenly moving out at 10,000 kilometers per second. Yes?
What's the trigger event between the Earth size and the 10-kilometer size?
The trigger event is that the density of this material gets so large that it's being held up by electrons, and actually degenerate electrons, and that those electrons, when they become relativistic, they're moving at the speed of light. That's when you have this crisis. And that's what defines this mass, actually.
The electrons strip off and then it just goes down.
The electrons are all totally stripped all the time in this whole star. Okay? So you have this bad day. You're moving out at 10,000 kilometers per second, and all of this material leaves. And that's good, because that's where the helium, the carbon, the oxygen, the silicon comes from. Okay?
Wait, where are you moving to when you're moving that fast?
You're moving into the galaxy, and so you look at the arrow. Arrow tells you where. So here's a supernovae, 2005 CS. I'm not going to explain the naming scheme. You can figure it out on your own. In a galaxy, Messier 51. So this is the before and after, shall we say. So here's suddenly a very bright event. This star, quote unquote, which was not there in the prior image, suddenly appears. That's what we call a supernovae. Novae was the first name for a new star. And then, of course, the scheme, actually, I don't know the full history, but in astronomy, we get desperate, so we call it super when it's bigger than the last one we saw.
That's the difference between two images?
This is an image.
It is an image?
Yes, it's not a difference image, it's a straight image. So this is the supernovae here.
The little black dot?
Little black dot, yeah, this little black dot. Yeah, as they say, just...
It goes from an iron BB over there to this thing on the right.
No, you can't, it's not visible here as a separate star, you can't see it.
It's basically an iron BB over there just before it explodes.
It was a star roughly it was a star like this.
Yeah, but as it collapses down, it becomes the iron core instantaneously, and then it becomes the nova that you see in the second picture.
That's right. And then the artist's impression of the bad day, which has nothing to do with reality, but it's a cool movie.
Do it again.
Do it again.
The stuff bounces off. It's not passing through.
So there's an ejection of material out into what we call the interstellar medium, the space between stars. In our galaxy, the next star over is about a light year or so. And the density of the medium around us is very low. It's about 1 particle per cubic centimeter on average. And so that's what this sudden ejection goes into, a very diffuse medium. Okay, what does the observer see? Well, I'm not going to explain this plot, but this is what the observer sees. They see a supernovae, or days since explosion, and this is brightness, and I'll put this in a more familiar unit in a moment. These are many different supernovae from many years, and these are called type, you don't have to know the nomenclature, but let me just say it anyway. Type 2P, P for plateau. You might know it as a plateau. So this is brightness for about 100 days. It's sitting at a certain brightness, and then it suddenly changes, and this is the typical core collapse. These are called core collapse supernovae. The energy source was the collapse of that ball at the center. Okay, so these are all the different ones. Here's the theorist version of all those data. Flat line, and I've put now in luminosity in units of a solar luminosity. So these events are roughly of order 10 to the 9 times the luminosity of the sun. Wow. All the stars in the Milky Way has about 10 to the 10 stars like the sun. So this is the luminosity of the Milky Way here. Okay?
So it's just 1 over magnitude down.
I'm sorry?
1 over magnitude down, that's right.
That's right. And so in that image...
What is it that causes the incredible increase in luminosity? I understand.
That's what I'm going to explain to you.
Okay.
Yep.
All right.
I'm going to derive this number, real time, almost real time. So that's exactly the right question. Who told, why is it that number? Why isn't it 10 to the 5? Why isn't it 10 to the 10? Why is it this number? So that's what I'll derive this number for you tonight.
And we're talking about stars with solar masses 10 to 15 times the sun's?
That's correct. Typically 10 times.
Things going on in other 100 solar mass stars.
Stars are born with a range of masses. The sun is typical. Stars as massive as 50 to 60 times the mass of the sun are known. That's about it. And then they go all the way down to very low mass objects. But when stars are formed in galaxies, they're formed with a wide range of masses, but there is a typical mass, which actually is the sun. The sun is pretty typical.
When you're talking about this at 10 to 15, that's not typical.
That's not typical, that's correct.
And where does a 1A supernova fit into this scheme?
4 slides from now. Okay? Okay. So it's advertised as a chalk talk. So I'm going to explain this luminosity. So so how do you understand this explosion? Well, the star was sitting down here, some very small radius, right? It suddenly ejected, the whole object went out at roughly the speed of 10,000 kilometers per second. And so at some age, some time later, it has some radius, which is going to be the velocity it was sent out at times time, where this is the age. By age, I mean days since explosion. Okay? So it's just freely expanding. And it's because the medium out here is so low density that it's not really running into anything. It's more or less running into vacuum. So it's just freely expanding. Okay? So in here are particles, that star, whole star, right? So there's protons, helium, all those nuclei, plus of course electrons. It's very ionized, and there's also photons. When you send that shock wave through, the material gets so hot that most of the energy is actually in radiation, in photons, not in the particle motion, but rather in the photons. Okay? So what Dave asked is, how do I get the luminosity? How can I get the luminosity? So I have this expanding ball of radiation, photons, but it's in this medium which has electrons, protons, and helium, et cetera, and as a function of time, this thing's just expanding very rapidly.
What about gamma rays?
Yes, gamma rays are photons. These photons are roughly at the temperature of this medium, and this medium is not that hot to make what you would call a gamma ray, which is sort of MEVs. So this is typically 10 to the 5 Kelvin, and then it's cooling, as I'll show. As this expands, it cools. Everybody knows, I think, or the opposite case maybe, is that if you have a gas and it's expanding, it's going to cool, or the vice versa case. If you compress it, temperature is going to rise. This thing's expanding, so the temperature is dropping, and I'll actually show that. Okay, so what's the problem? The problem is, if I want to see this, right, I have to get the photons out, because that's what I observe. I observe radiation. I don't observe this gas. And the problem is that for the photons to get out, it has to random walk through this stuff. Okay, so here's a random walk. I just pulled off the web. Right? So imagine these are photons. The color scheme has nothing to do with anything. So these are just showing you what a random walk looks like. So imagine this box is my star. Okay, slightly change of geometry. And these photons are trying to random walk out. Right? They're trying to get out. So the question is, when do they get out? This medium is expanding. So when do you think it's easier? At the beginning or at the end? You have a smaller distance to go at the beginning. That's correct. But at the beginning, is it a denser medium or a less dense medium? Okay, so we've got denser medium but smaller radius, so it doesn't have to go as far at early times. Late times, density is much lower. It's easier to get through, but you've got to get through a larger radius. Right?
You get released at the
The
end.
America would have stayed about flat, wouldn't it?
Well, that's what it did. That's what I was thinking.
Okay, so we don't have to guess. We can calculate.
If it expands, you get less radiation per square inch, but you have more square inches. So it's
okay.
split.
Right, so the photons were basically created at the time of the bounce, And they've been trying to get out ever since?
That's more or less fair, yeah.
Okay.
More or less. Okay, so how do you understand this in a little more detail? Well, you have to understand, as these photons are moving around, you might notice I'm drawing a characteristic length that they tend to scatter. Well, let's get one that gets out. Almost. Okay, there it goes. Okay. So there's a characteristic distance I've drawn here, which was what we call the mean free path. That's the average distance it goes before it scatters again, right? This is you on the sidewalk. How often do you bump into someone? There's a mean distance you move before you hit something. That mean free path is inversely dependent on the density. If the medium is very dense, of course, you don't go that far. So it's 1 over the density of the medium. This is rho. And then you have to have some probability in that medium that you have a scattering, or which is what we call the opacity. So you don't need to worry about this thing, but this is just a number, kappa. So this is what we call the opacity. It's how opaque the material is. If it's very opaque, the mean free path is very short. Okay, this is the density. The density is just the mass of the object divided by the radius cubed. That's the density, how many grams per cc there are. Okay? So far so good. We're almost there. What I have to calculate, though, is how long it takes for this random walk to get out. Right? And you might notice that it's much longer than the time it would take a photon to just traverse and leave. Right? The time it would take to just get out, if it just had to traverse this r, just the escape time, call it, right? That would just be the radius divided by the speed of light. Okay? And that would be fast, because this material is moving at 10,000 kilometers per second, but that's still less than the speed of light. So the photons would just leave if there was no scattering. Right? But that's not an option. So how do we understand the difference in the distance it has to travel? Well, if I want to get out, I'm going to have to scatter so many times. So there's going to be n scatters. I drew it here with n of 50. You can see here these have, I don't know, some very large n. And does anybody know how far you move if you're randomly bouncing around right to left, right to left, right to left?
Square root again?
Get to ask a political question. Nobody got the joke. Okay. When there's an election, you always see the error bar on the polls. Yes?
Square root of n.
It goes as a square root of n. So if you see a 10% error bar, how many people did they talk to? 100. Okay? You should always remember that. Right? Okay. Because you might want to ask which 100 did they talk to. Okay. So the distance I have to travel, right? The distance I've moved, this L, is going to be the square root of n times the mean free path. Okay? The time it's going to take me, which I'm going to call, actually I defined it up there, but I'm going to call it the diffusion time, is then going to be the time it takes me to go one step, which is a mean free path divided by the speed of light, right? Times a number of scatters n. Okay? And so if you do this, I'm going to put this up on the board, then this goes like r over c times r over lambda. So it is longer than the escape time, r over c, by the ratio of the radius of the object to the mean free path. Okay? All right, so that's our random walk, and that's my only real need to use chalk tonight. Okay, so I'm going to leave that up and then show you what this gives us, because this actually gives us the answer to the question of when does it go out. So I just derived for you this, which is the diffusion time, the number of scatters times the time between scatters, which just scales this way, r squared divided by the mean free path in c. And if I put in for lambda that equation I derived over there, I actually find that this diffusion time goes like the opacity, which is just a number, times the mass of the envelope, divided by the speed of light and the radius r. And so now we can answer the question of whether this diffusion time gets shorter or longer as the radius increases. Well, you can see it. As the radius the only thing changing in this formula is the radius. As the radius increases, the diffusion time gets shorter and shorter. So it's easier to escape at late times. So at early times, the radiation's not escaping. It's just trapped. Okay? But then there's a characteristic age. If I set this, I can ask, at what day does the diffusion time equal the age? So on day 1, the diffusion time is 100 days. On day 10, it's 10 days. And oh, that's interesting. On day 10, it's 10 days. Right? So if I equate those two, I calculate at what age the diffusion time equals the age. That sort of mental thing I just did. And that just gives me this magic formula, which is something like 10 to 20 days. It depends. And this is all tilde physics, so really there should be numbers in here, 7s and pi's and et cetera, et cetera. And so at early times, this ball is expanding. The radiation can't get out. And so its temperature is dropping just due to what we call adiabatic expansion. It's dropping like 1 over r. So the temperature in that plasma is just declining with increasing radius. So I haven't gotten the luminosity yet. Almost there. Okay? So I only have 2 pages of algebra. So everybody with us so far? And we're calling this simple light curves, by the way. That's the okay. Okay. How do you estimate the luminosity? Well, now you got to believe me a little bit. It's the same way I calculate the heat loss from your house, which is I'd ask how hot is it inside, how hot is it outside in terms of temperature. I then go and find the R value for your poorly insulated California home. Okay, that would give me the flux, how much heat per unit area is leaving, and then I multiply it by the area of your house. And I give you, bad for your single pane windows, better for the place you might have placed insulation. And so there's some area. So here's the area, r squared. I'm dropping 4 pi's. Okay? Here's the gradient, the change as a function of radius, in this case, of the temperature. So if it's hot inside, this is that term. And then this is the R value, which is just what we call the opacity again. How good of an insulator is it? And if you just do the tilde physics for this, what you find is that, not too surprisingly, it's the total energy this is the energy density in radiation times the volume. So this is the total energy in photons, divided just by that diffusion time. That's the luminosity. It's sort of intuitive. It's the total energy in the radiation field, and 1 diffusion time it's going to leave, so that's the luminosity. Okay? So we're almost to the number. At early times, this temperature I already derived just changes like 1 over the radius as the expansion occurs. And so I can plug that back in and put in the initial data, the initial radius of the star. So this is the important point. The initial radius of the star when it got hit by that shock wave. The initial temperature at that point when it got struck. Those matter because that sets my temperature scale. Okay? And if I carry through that algebra, now you just have to trust me on my algebra, that this number I get for the luminosity is actually just a number. Here's the mass of the total mass, the opacity, the speed of light, the initial radius, and the total energy in the supernovae, the energy in that shock, a number like 10 to the 51 ergs. So that's the luminosity. And you might notice that in this calculation, time is canceled out. The radius has gone away. So yes, the radius is changing, but this quantity ends up being independent of time. That's why the line is flat. Okay, so I've derived 2 things. I've derived that the line's flat, and I've derived the value of the line. Okay, and this works. I mean, this isn't just a story. And you can do this in much more sophisticated ways and find slightly different dependencies and get the 2 pi's, et cetera, et cetera. And this agrees with full numerical calculations to sort of within 10%. So that's, for astronomy, that's good enough. All my plots are log, right? I got 3 orders of magnitude. So if I'm 10%, I'm happy. So this explains that luminosity, but you have to know what R naught is, right?
That's the radius before
the radius before the explosion. Before the explosion. And so all of those supernovae that have this value have an R naught that's about what we call an astronomical unit, the distance from the Earth to the Sun. That's because when they blow up, that outer radius is actually of order what we call a giant. Okay? So this is the answer. And when those events are over, you've made something sitting at the center, which is that ball that collapsed, that iron ball that collapsed, which most often makes what we call a neutron star. Okay, here's the Crab Nebula from the supernovae that occurred in 1054 AD. This is the ejecta, all that material that's been sent out. This is an X-ray image. And this neutron star is sitting there spinning at 33 millisecond spin period with a very strong magnetic field. The units aren't going to mean anything to you, but about 10 to the 12 times that of the surface field of the Earth. Okay? So that's all of stellar evolution and all of core collapse supernovae. Okay, we good?
Pulsar, right?
And that's a pulsar.
Question, opacity. I might think intuitively that it would be related to density.
It's property of the matter. Doesn't relate to the density. It's how opaque it is per gram. Yeah. You're very opaque. Can't see through you, right? And you're right. Whether I can see through you depends on how much of you there is, but it also depends on how opaque you are, right? Okay. So let's go back to this image. So this is again the Pleiades open cluster, the seven sisters. And what you may not know is that out of the bright stars, the bright ones, right, these three are binaries, or sometimes triples. Okay? So half the stars on the sky, roughly, are in binaries. And that makes a big difference and actually gives us another way to make supernovae. So the core collapse events I showed you are what we know happens for stars that are more massive than about 10 times the mass of the sun when they're born. Stars less massive than that have a different outcome if they're isolated. And this is the outcome for an isolated star like our sun. By isolated, I mean there's not a stellar companion. We're mincemeat when this happens. Okay? All of those objects, stars less than, I'm sort of being 6 to 8 and 10 of the same number for this discussion, end up being able to burn hydrogen to helium, helium to carbon and oxygen, but at that point they can get no denser or hotter, and actually they cannot do fusion beyond carbon. And so they make an object, what we call, as we call a white dwarf. It's got the radius of the Earth, central density of about 1 million times that of water, and they just cool with time. And so this is a young white dwarf sitting at the center of what's called a planetary nebula. This is material that went out in a very slow wind, only roughly 5 kilometers per second. That's slow, right? I was talking about 10,000 kilometers per second earlier, so across the Earth in a half a second. This would take a long time, 1,000 seconds, 3,000 seconds, so an hour, the length of this talk to cross the Earth. So this is the case if it's isolated. However, as I showed you on this other slide, roughly half the stars in the skies are binaries. And so you can get a different outcome. This is an artist impression by Tony Pyro, who was a graduate student here at UCSB with me. I didn't realize his artistic talent until far too late in his graduate career. And what can happen when you have stars in binaries, you can make one of these white dwarfs. It can be sitting here, and you can bring a star in as a binary that's so close that it pulls matter off. That matter spirals down and tries to accrete onto this object. And that accretion and reheating and increasing the density can actually restart the fusion in this object. And when it does that, it's actually quite an explosive event. And that's the other energy source I want to talk about tonight, which are those events that are powered by the thermonuclear energy, which are called type 1a supernovae, which someone asked about. So all you do, quote unquote, we actually don't understand this, okay? All you do, quote unquote, is add material to that object which was already very dense, and when the burning starts to go, it actually can't shut off, because as the temperature rises, it's at such high densities, as the temperature rises, it actually doesn't change the density at all. It doesn't change the pressure at all. Very counterintuitive. And because of that, you get a thermonuclear runaway, and that material burns all the way to nickel-56, which I'll explain in a minute, in about 10 seconds.
The entire star?
50% of it. This is the fate, roughly, of about 1 in 500 white dwarfs, and actually over 2/3, probably more like 3/4 of the iron in your body is made this way. Now I said iron, not nickel, so let me first explain why it's nickel. This is carbon and oxygen. This reaction happens so fast, in 10 seconds, that there is no way for neutrons and protons to change amongst themselves. And so the most stable isotope with equal numbers of neutrons and protons is nickel-56. So that's what you make. As I'll show you, this is unstable, decays to cobalt, and then to iron. And so this is where the iron's made. Okay? Yeah?
This is probably a stupid question, but how does it get in your body?
This material gets sent out into the interstellar medium, gets mixed in with the gas, and when the next generation of stars are formed, that iron is in that gas. Some of that gas gets formed remaining in a disk around the star. The remaining disk around a star makes a planet. Planet makes you, and there you are. Okay? Happened a while ago. Okay? So this is a type 1a supernovae. It's bright as a galaxy for a month, this event. And you can already see from this that it looks a little different, looks a little more extreme than the other image. Yeah?
Is there any difference between first and second and later generation stars? Because the later generation stars start with some of the heavier elements?
Yes, absolutely.
How does that demonstrate itself?
So the first generation of stars, you're absolutely right, only had hydrogen and helium in it, nothing else, more or less. And that generation of stars, we would like to find examples of those still in our galaxy, because if it was a very low mass object, they burn so slowly it could still be around. Like all things in astronomy, we name them to confuse everybody. That population is called population 3. Okay? And we've never found such a star. Okay? There are some stars we see that have very small traces of heavy elements, about a part in 10 to the 4 relative to the sun. Those have been only found in the last 10 years. And those are the stars that look like the most primordial, but we've never found a star that's really the primordial stars.
I mean, heavy elements, what are the heavy elements?
To an astronomer, everything above helium is a heavy element. And it's even worse, we call them metals. So we call carbon a metal, we call oxygen a metal. It's really bad.
Well, Lars, from an astrophysical standpoint, though,
yes.
How would these stars behave differently? And when a current generation star is created, what is the proportion of heavy versus light? So
in the sun, about 2% of the mass of the sun is made of elements heavier than hydrogen and helium.
So it's not really...
Yeah, only about 2%. And you're right, each generation is richer, shall we say, in those elements as it goes on. And in some galaxies, it can maybe be about twice that, and that's about it.
Are type A, 1A supernovae still used as standard candles?
Oh, absolutely. Yep.
Distance, they're still
and I'll briefly note that.
Okay.
But, I'll do a quiz. Yeah.
At the time of the diffusion or the explosion, does it just steamroller any part of any particle in dark matter, or does it interact in some way?
There is dark matter in all these galaxies, but on the scale of these phenomena, that dark matter basically has no influence. Yeah, it does just go right through it.
On your mass 15 star, what percentages do you have for iron, oxygen, etc.? Because you're saying that the scattering events reform stars, so that would imply that a significant amount of that is still hydrogen or helium.
Yeah.
So do you know about what those...
I mean, for a 15 solar mass star, that diagram I showed was about right, which is the outer 10 solar masses is more or less the same as it came on, lived on the star for 5 million years, but didn't get to burn, got sent back out. And it's the same for the sun. I mean, for the sun, roughly half of the mass in the end is not going to burn. It's just going to leave with no, it was just there to provide pressure. Right? So like your neighbors, yeah.
When we're counting one supernova to, what is the distribution? Is there a...
It's about 50-50 of these two types. For no good reason. Didn't have to be that way, but that's more or less how it turned out. Yep. Yep.
For not finding a population 3 object, is
Yeah.
what role is better increased technology going to play in that, or is it some other variable that's the lack of discovery?
I mean, I think the biggest breakthrough has been a theoretical understanding that tends to make us think that the first generation of stars were only massive, and that we actually didn't make low mass stars in the first generation, in terms of how star formation happened very early in the universe. But we'll keep. I mean, the observers will keep looking. Okay, so I'll put this into my theorist plot in a moment. But these are the type 1a supernovae. This is time on this axis. Here's my 10 to the 9 times the luminosity of the sun, a typical galaxy. This is a log plot, so this is a full order magnitude up to here. So there is a spectrum of brightnesses of these events, from brighter to fainter by about a factor of 10. Someone asked about using these for cosmology, and it's true, you can do that. To do that, though, you have to decide whether what you're seeing is one of these or one of those. So the question for the audience is, how would you decide which one you're seeing? Do you see any difference? The slope. Where do you want to measure the slope, David?
Anywhere you want.
Anywhere you want. Okay. Right. So what he's pointing out is that the bright one decays more slowly than the faint one. Everybody see that? Yeah. That phenomenological result is what you need to do to use these for cosmology, because that you can measure. You can measure how long it takes to go from its peak to a factor of 2 down. And then you correct and say, well, it decayed fast, so it's one of these guys. Okay? What causes this variety is still under active debate. We certainly know that the peak luminosity is set by the amount of nickel you make, because the nickel is the radioactive power source. So how do we get... So back to this plot I showed previously, here was the core collapse event sitting here. Now I've drawn on a typical thermonuclear event, and there it sits. Again, I will just tell you right now, there's no reason these two had to have the same luminosity. By same, I mean they're on the plot. Okay? I mean, yeah, it's a factor of 5 different, but it's the same number. Okay? Didn't have to be that way. So why is that? So we could do the same calculation I just did. The difference is this R naught is very small. That initial explosion radius is the size of the Earth. Okay? So that would be a very faint event. So that's not the explanation. The explanation is that I make these radioactive elements, nickel, which has a half-life of 6 days, decays to cobalt with its half-life of 78 days going to iron. And it's this radioactive heating that actually sets the luminosity. So it very quickly gets into the regime where the diffusion time is very short. After about 20 days, I'm in this regime. Here I put a factor of 7 in to make everybody feel better. And call it equals. Okay. After about 20 days, the time it takes the radiation to get through is shorter than the age, and so if you have a heat source, this is your furnace burning away, right? You go outside, you integrate all the heat leaving your house. Guess what? It matches the rate at which you're generating heat in your furnace, right? You're not heating the house. You're not heating the house. Okay, so that's what these are. And so that luminosity in the peak is just set by the mass of the stuff you make, which is about a half the mass of the sun of nickel. And so it's just a complete accident that if you take a half a solar mass of nickel and ask what its luminosity is, this is what the value is. Okay?
On that diagram, the purple starts at 10 to the 8th on the left-hand side of the diagram. So is that all visible going to the peak, and the red line is a sudden burst of energy? No, unfortunately. So two things. It's we don't know. Let me go back. So here, there are very good data now, not on this plot, that do get down to about, the peaks are typically about 18 days after the explosion. There are some data that come very early.
To do that,
types.
Sorry?
On both types.
On these types.
Okay.
Because these are bright. On the other types, they actually are not that bright, so it's very hard to get early time data. And you might have noticed from that plot of what the data look like, a lot of these, I mean, they don't actually know the days since explosion, right? Because you can see here they just have suddenly this thing turned on. Sometimes it's quite often hard to know where to put your first data point depending on your sampling. So you'll see that the rise is usually not resolved. None of these have a resolved rise. That's what you're asking. For none of these do you see the curve come up in terms of data. That's starting to change. But
well, the question is whether or not the energy, you were talking about the random walk, whether or not there's a qualitative difference between the two types of explosions where there would be no random walk or less of a random walk in one form rather than the other.
The calculation I did is, there's no way from this calculation you could actually get a rise. I calculated a pure number. Right, and so that is part of the answer is that this rise is extremely rapid. The physics of the other is different. Because it's the heat source here is the radioactivity in these light curves. Okay, so I don't know if okay, so as I said, complete as I say accident that these two numbers are the same. Now, if you're a theorist like myself, you should say, well, how bright could things be? How faint could things be? I've described these two numbers, but I've shown you enough theory that you could say, well, R naught could be small. I can make a really faint object if I wanted. Maybe there's another energy source I can tap, make it even brighter. Okay? And as I'm going to briefly show you, that's now happening. Because as I mentioned, these two we've known about for 30 years, but we're starting to find other things. And I sort of want to wrap up. So why are things changing today? Or let's say in the last 5 years. One is somebody asked about the use of supernovae for cosmology. That absolutely motivated and rejuvenated the field to go out and find supernovae because people wanted to use them for cosmology. And because of that, there are many surveys that have happened. So something called the Sloan Digital Sky Survey ran a supernovae survey for about 3 years, finding about 600 supernovae. There's a project coming online about now called Pan-STARRS-1 on Haleakala, which is about a 2-meter telescope. And what I want to emphasize a little bit more is the project I've been involved in, which is called the Palomar Transient Factory, which is a collaboration. So here are all the collaborators. So the local collaborator is the Las Cumbres Observatory. This is a project led by Sri Kulkarni's group at Caltech, where the game was to take the old 48-inch telescope at Palomar. That's a telescope that did all sky surveys with glass plates of about this dimension physically. You can now buy a camera, in this case an off-the-shelf, literally, not quite on eBay, off-the-shelf camera that had been used on the CFHT, a telescope in Hawaii, that was about this physical dimension with CCDs of 100 megapixels. So all of you have digital cameras. Who has a 100 megapixel camera? Okay, we got one in the back, yeah. Okay. So the reason the fields changed is twofold. One is that because of industrial advancement, shall we say, you can buy 100 megapixels at an astronomer's price point. Okay? So that's one thing that's changed. The other thing that's changed is that you can deal with the data of taking an image with that camera, let's say every minute, maybe every 10 minutes. And you can deal with all the data from that for many nights, for many years, because you can now manage those data sets. So those are the two things that have changed. And that allows you to do things that you couldn't have done 10 years ago. So in particular in this project, it's roughly scanning about 10% of the sky every week. 10% of the sky every week.
The same 10%? The
same 10%. So you look today, you wait a week, you look again, and then what do you do? As a theorist, I say, well, you do the simple thing, you just subtract the two images, right? Well, observationally, that's a challenge. But if you subtract the two images, you will find something that is on that was off before, and vice versa. And the volume of the universe that you can sample this way is now such that you can indeed get this 10 per day of supernovae. We're still only looking at 10% of the sky. They last long enough that I should be getting 10% of the sky in one day. How many seconds are in a day?
A lot.
A lot. Right? 86,400. Okay? Right? So 10% of the sky, so that's 8,600. We're getting only 10. So we still have a lot to do. Right? So that's good. What I'm going to sort of wrap up with are two things that we've done some theory on, because I do want to stop, of weird events. Very bright events and very faint events. Again, you shouldn't be surprised. The observers are going out and looking at a lot of things. We're going to start finding the rare events. Now, the first rare event I want to talk about are very bright events. And they were first found by this dinky telescope with a whopping 18-inch diameter called ROTC. And this is just the paper that was done by Robert Quimby. And then also a collaborator at the time was Eli Rykhoff, who's now here as a Tabasco Fellow here at UCSB. He was the person that actually built these cameras, a lot of the work. So this was a rapid response telescope for doing other science that they decided, well, let's do a supernovae survey. And it had very little volume compared to everything else I'm showing, but it found very bright events. You can't tell at all from this plot that it's a bright event. It's 18th magnitude, which probably doesn't mean much to you. Your naked eye, if you're lucky, in Santa Barbara can maybe see to 6 magnitude. That's 12 magnitudes, which is a big luminosity difference, on flux difference on the sky. But let me show you what these are on the scale of the others. Skip that. Well, there's now, you find one, guess what? Once you've found them, other people find them. If you've got one, they've got one. That's called stimulated emission. So there's now a host of these, and Palomar Transient Factories found them. And they have peak luminosities that are quite high, 8 by 10 to the 10. So if I put them on this plot, which is really what I want to do, there's an example. Okay? So, who ordered this?
What are those things?
Those are question marks.
What is the thing that's generating?
Well, I'm going to give you our theory. Okay? The sociological thing that's very interesting is that survey had the smallest volume on the sky. There is no reason that survey should have found these objects before others did. Reminding you that people still matter, because somebody was smarter than somebody else. I'm not going to name names. But also he had an advantage, they had an advantage because they had a small volume. They actually didn't have a lot of supernovae to study. So everything they got, they studied. And for that reason, sometimes you find something. If you have 500 of them, you have to decide where to focus and whatever. So it's very interesting. That's why I said there's stimulated emission, which is there are now many of these known. They're from galaxies where stars are being formed. That just tells us they're from massive stars, so that's a clue. They are 100 times brighter. You can see right here, it's 100 times brighter than the typical core collapse. We only have 6 of them, roughly, so it's kind of hard for me to tell you how frequent they are, but we're not shy. With 6, we can do statistics. So they're roughly, probably less than 1% of all the core collapse events. So they're rare. They're very rare. Okay. So, when I saw these results, let me tell you what I knew. I'm going to close with this. I knew, because I'd convinced myself it was true, I knew this formula. Okay? And if you want to make something a factor of 100 brighter with this formula, you've got to make R naught a factor of 100 bigger. There's no star that big. So that's not an option. I can't make the mass a factor of 100 smaller, because it would be 1/10 of the mass of the sun. Those stars don't explode. I can't change the speed of light. The opacity is a pretty well understood quantity. I can't mess with that. But I could try to increase the energy of the supernovae. If I increase that by a factor of 100, I actually have a very hard time understanding the energy source, because it's getting bigger than the rest mass of the sun. Okay? So that was a clue that something was different. Okay. So that's clue 1, something different. Clue 2 is it's only about 1% of the events. It's not all the events. It's 1%. Okay. So I've got this fuzzy image, another press release image from NASA about weird things called magnetars. I showed you at the beginning of the talk that when you have core collapse events, you make these little neutron stars, 10-kilometer objects with a magnetic field, which I kind of didn't talk about, of order 10 to the 12 Gauss. Well, through a series of observations from roughly the last 20 years, we know, and I'll explain in a minute, that roughly about 10% of neutron stars are born with magnetic fields that are much higher, a factor of 100. Now, these are hard numbers. What does 10 to the 14 Gauss mean? I don't know how to interpret it for you. But you can go on the web, which I did today, to try to find an analogy. So many of you probably have credit cards. So the statement on the web, which I've not checked, is a magnetar roughly at the distance of the moon. If you put a magnetar at the location of the moon, the magnetic field strength would clean your credit card. Now, it doesn't make me feel like I understand the number any better, but okay. So what's interesting about these objects is if you have one born and its magnetic field is not aligned with its spin, then as it rotates, it radiates the angular momentum of the spin out in electromagnetic waves, and that allows you to now tap rotation. So because it's very magnetic, I can tap the rotational energy of that object. And that's my last message tonight, is that I'm going to tap the rotational energy. I've talked about gravitational energy, I've talked about nuclear energy, and now I want to tap the rotational energy. But to tap it, I have to do it at the right time. Okay? Everybody with me? So, if that thing is born spinning at between 2 and 20 milliseconds, which we don't know, that's the hypothesis we have to make, the conjecture we have to make, then that spin-down energy will actually deposit energy into that envelope on a time scale of sort of days to months to years. I've deleted the formula because it wouldn't help you. So how does this help? This helps because that envelope's expanding out, temperature's dropping. If I now can have an energy source at the center, I can sort of rejuvenate and bring the temperature back up and break my formula. But by breaking that formula, I can actually get high luminosities. So this was work that I did first analytically, and then got Dan Kaysen involved, who's a postdoc at Hubble Fellow at Santa Cruz. And the two of us did this work. And then science is always interesting. Sometimes it's exciting. Stan Woosley, who is Dan Kaysen's mentor at Santa Cruz, had the same idea. Sent Dan Kaysen an email. Dan Kaysen sent me an email, says, we better write this up. The guy in the next office over has the same idea. Stan is very gracious, and so we all agreed to publish independently simultaneously. So it had a happy ending, but also it tells you that sometimes the ideas are indeed in the air, because Stan had not talked to us, and vice versa. So this works theoretically. And what we do is we just change this formula. So here's my formula that we all know and love now. I just basically start over. I have the explosion happen. I let the object expand out to a new radius, which is the velocity of that expansion times the time it takes me to spin this object down. So that's the new radius. At that new radius, I now deposit the spin-down energy, the rotational energy of the neutron star. So this is my modified formula. This is what I guessed analytically. And what it tells you is basically I can sort of get a new effective R0 by just letting that object expand out and then dump the energy in at late times. And so even though the spin-down energy, the rotational energy, could be much less than 10 to 51, I can totally screw up the light curve. And I can actually naturally get these high luminosities. Yeah.
Lars, the spin has to be created at the time of the collapse.
Right.
Isn't it?
That's correct.
So so the energy had to come from the collapse.
Yes. Yes. It's just, but I want to tap it. The way to think of it, right? Let me just say it. If I tap it very early, it doesn't help me at all because it just changes this number by 5%. If I tap it 10 years later, the event's over. So I have to get that energy to come out on some time scale of days to weeks to months to affect the light curve. To do that, I have to have this magnetic field strength. And we know those stars exist.
So what has created the magnetic field strength then?
No idea.
That's somebody else's problem.
Oh, that's independent of the rotation.
Okay.
Well, yeah.
So this works. So Dan started running 1D calculations. This is just to show you we actually did a real calculation. You're supposed to be impressed. Okay, real calculation. This would be for a very weak amount of energy going in, and then as you crank up that internal energy, you basically just increase the temperature and that as you increase the energy. And again, if you increase the temperature, it's going to be brighter. It's hotter in the middle, right? It would have been this value. Instead, it's this value. And it goes as t to the fourth, okay? So that's 2.5 and 0.5, that's 5. 5 to the fourth is? Oh man, okay. 625, thank you. Okay, so it really works. This is just to impress you further. Basically, we can change the spin. We don't know these things, so we have some free parameters. Now, we understand it well enough, though, that if you give us the peak luminosity and the time to get to the peak, we can back calculate what's the initial spin and the initial magnetic field. So I skipped all that. We can predict it. Not predict it. We can post-dict it. We can do that by hand. By hand, I mean analytically. The advantage of that is we don't have to run all these models. Okay, so I'll skip all that, but all I'll show you is the plot that made us say we better write the paper, which is this plot. Which is you do it by hand, and that tells you what the magnetic field and period should be, 2 × 10 to the 14 Gauss, 2 milliseconds. Then you run the code, and you get the black line, and the black points of the data. Now this is too good, right? It is too good. But don't forget, we're astronomers. This axis is actually the logarithm of a quantity. Okay, so these are off by a factor of a fair amount. Okay.
I wonder if that means.
Yeah. Okay, so that's just to sort of impress you. Okay, so I'm going to skip the last thing on faint because I know we're running out of time. But I'll just stop there and just say, what next? We don't know. And I'll take any further questions. Thank you.
Is that big? Is there something to measure that tells you?
They actually measure the spin down. They actually measure the rate at which they know the period, and they measure the rate at which it spins down, slows down, and because of that, you actually infer the magnetic field. Yep.
So where do the elements heavier than iron come from?
Okay, the elements heavier than iron are made. Let me give you the quick answer. When the shock wave hits this material, there of course is a little bit of iron in this stuff because it was made in the other generation of stars before that. Okay? There's reactions when the shock wave comes through that make free neutrons. So if you have iron and you have free neutrons around, the neutrons will capture onto the iron. And so it's a series of neutron captures on iron. So you have to start with a seed, iron, and you throw neutrons onto it. As you throw neutrons on, it becomes so neutron rich, eventually a neutron in the nucleus goes into a proton, and then you can keep adding more neutrons. So that gets you, go as far as you want if you have enough neutrons. So it's neutron exposure. Yeah.
Interesting.
Had you mentioned what the temperature is inside the resulting neutron star?
No. Depends on the age. At 100 years, the temperature inside the neutron star is about 10 to the 9 Kelvin. It's cooled down a lot. It was at 10 to the 12 at birth.
What happens at the boundary between one of these explosions and the black hole? In other words, what is it physically that allows the black hole to occur and not?
Yeah. Okay. So all of the stars die in the way I said, which is you form an iron ball. What I didn't go into details on was this iron ball, more or less, doesn't depend on the total mass of the star. So if this was a 50 solar mass star, this inner part would look roughly the same. So the simplest answer is that this iron ball collapses. It releases a certain amount of gravitational energy. That gravitational energy sends out a shock wave. Well, if I've got 30 solar masses out here instead of 15, that shock wave might not successfully unbind everything. It might not have enough energy to send this stuff out, in which case a lot of this material does collapse further onto the young neutron star, and there's a maximum mass neutron star of around 2. So if you try to dump all this stuff onto that neutron star, you will form a black hole. And that's more or less our understanding.
So it's really a
failed collapse.
Go off of the, back toward the core.
Yeah, so that maybe this stuff leaves and this stuff stays and comes back down. Yeah, yeah.
Does the spin of the star have any significant effect other than the magnetic connection?
Not that we know of.
So there's not enough angular momentum outside of the magnetic field to create any disturbance in the collapse?
I mean, maybe. I mean, there's still a lot of debate going on because of other events called gamma ray bursts, where we seem to form jets of material coming out that actually, believe it or not, penetrate all this stuff before the shock wave gets there. So that might be tied to rotation, because you want to have something that's doing that. Yeah.
What about the temperature inside a white dwarf?
Depends on when you ask. At birth, they're around 10 to the 8 Kelvin. That was the temperature you needed to burn helium to carbon.
Right.
And then 10 billion years later, it's at about 3 million Kelvin. So not T equals 0.
Yeah.
Yeah. They're cooling, but they're not there. Yeah.
At the beginning of the core collapse, I think you said something like the electrons become relativistic.
Yes.
So they weren't relativistic before?
Right.
And what does that mean, to be relativistic?
It means that the particles that are moving, the electrons, have an average speed, which is approaching the speed of light. Or their energy, their kinetic energy, is getting comparable to their rest mass energy. That's the.
So they're just getting faster, basically.
Well, but there is a the speed of light thing's real. So, yeah.
Is the fate of the sun still speculated to be a brown dwarf?
White dwarf.
White. It's white.
Yeah, yeah. We really don't have much debate about it.
Can elements heavier than iron be made by fusion of other elements lighter than iron?
No. It is the case that if I have iron and I'm adding neutrons or protons, I can still release nuclear energy, but I can't take 2 iron nuclei. If I bring 2 iron nuclei together, that resulting nucleus will actually that'll cost me energy to make. So it's a loser at that point.
So you see me sidling up. Let me just quickly say, I'll try and be real fast. First of all, I learned that Lars actually has laryngitis. I'm amazed he's been able to even speak tonight, so thank you for saving your voice. I'm always incredibly impressed by the level of sophistication of the questions that members of the friends ask. It just blows my mind, so thank you for coming. One of the fabulous things about the KITP, one of the cores of the KITP, is the permanent members, and Lars is our shining star of the permanent members. I believe, Lars, that you've given at least 3 chalk talks. He's our stellar chalk talker. We honestly are incredibly fortunate to have Lars in our group, so please help us thank him. Lars, don't let us make you talk too long.
No, it's fine.